Hello, Jack Lansbach with NTOP here. I'm making a recording today to cover the topic of managing distortion via geometry compensation. We get quite a few questions from users about what kind of capabilities NTOP might have to help manage distortion via geometry compensation. And so we wanted to create this video so we have a resource that we can easily share with users. In today's video, I'll be going over the tools that we have to help with this and how they work. So let's get started and dive right in. So first and foremost, what is distortion in additive manufacturing? Basically, what we're talking about with distortion is the warping, shrinkage, and general change in shape that happens during the printing process. Normally, it seems most of the time I'm usually getting questions from people that are working with laser powder bed fusion and printing metal parts. In that case, residual stress inherent to the AM process is the major driver for the distortion that's occurring. This could certainly also apply, to polymer processes as well. But there's some other strategies and stuff that we'll talk about a little bit that we see employed sometimes with those types of processes. In general, distortion is not desired, right? It causes non-compliance. The part bends and twists or distorts out of the acceptable tolerances for the part. In certain cases, it can be extreme enough that it can actually cause a build failure. In some of these pictures that you're seeing here, we see separation happening, cracking, things of that nature. And that's also obviously something that is not desired and would cause a lot of waste and inefficiency in the manufacturing process. So basically, how do our customers use NTOP to combat this? So there's really two different ways that you can go with trying to combat distortion in additive manufacturing. Number one is starting with general part design. So obviously avoiding certain things such as full density or very large, thin-walled geometries, as well as avoiding sharp transitions between thicker and thinner cross-sectional areas. These are well-known design for additive strategies that are employed in the design stages of your part so that you have something printable that isn't going to cause problems during the printing process. Now, NTOP has some tools to help with that. We've got some custom blocks and things like that can automatically identify extreme changes in cross-sectional area by layer height, things like that. Workflows like that are completely feasible and possible inside NTOP. But that's kind of a different topic than what we're discussing here today. The other different topic is support generation, right? So lots of times people will create support structures that might be removable or maybe become part of the final part. And sometimes they're also just support structures that are very, very close to the part to act as like a heat sink and that sort of thing. These types of structures are also possible to design in NTOP. We've got a series of custom blocks for bar supports and volume support structures that are basically starting points. What I will say is that, NTOP is not a dedicated support structure generation tool. We have the capability to do it, and you basically have to spend some time creating your workflow that's going to create the type of supports you want. And once you get through doing that, usually it's quite reusable and you can reuse that workflow over and over again for different parts and that sort of thing. But, sometimes it takes a little bit of time to develop that initial workflow. So again, this is like a different kind of subtopic. if these are areas of interest for anybody, I strongly encourage you to look at through some of the other resources that we have available, as well as reach out to your customer success manager or to NTOP support and ask them about any kind of resources on those topics. What I really want to focus on today in this video is geometry compensation. So another method of dealing with distortion is what is called geometry compensation. And what that is essentially pre-distorting the original nominal geometry to have it distort into compliance when the print occurs. So you can see it over here on the right hand side. The original nominal geometry is this straight structure here with, it's like a comb-like structure, right? With some vertical slats on it. And what's happening during the process is it's becoming distorted in, for lack of a better term, a smiley face orientation, right? It's curving upwards when that happens. Well, if the process is very repeatable, meaning when you print 5 or 10 of these, at different times in some given additive process, and you see the distortion happening is very similar every single time, a really effective way to combat that is to compensate or pre-distort your geometry. So if we take this original geometry and we pre-distort it in the opposite direction and magnitude as the distortion seen, generally you'll see the distortion still occur, but because of that pre-distortion, it's now going to distort kind of into nominal compliance, right? It's going to distort and look more like what the original design intent is, instead of distorting away from that and ending up with the smiley face. So you basically create kind of the frowny face, distorted or pre-compensated part, and then when distortion occurs, you kind of end up with something right along the lines of what you originally intended. Okay, so let's take a look in the software at the 2 custom blocks we have to utilize for this, and I'll explain how they work. So what we have here is a medical device. It's a bone plate, okay, and this bone plate in purple is our nominal geometry. This is the shape that we want, right? And we want to get off of the printer. Now, we have 2 custom blocks. The first custom block is called Simulation Compensation Compensated UNV Input. The second custom block is called Simulation Compensation Displacement Point Map Input. I'll talk about the 2 differences here. The first one is to be utilized when you are dealing with data coming from a build simulation software. Specifically in this case, this custom block is designed to take a .unv file or files from Simufact. So Simufact is a build simulation software that's well known in the industry. It does a great job for the most part of determining for any given additive process, or the ones that it supports anyway, the magnitude and direction of distortion that's going to happen on a given part. Now, it can also actually create compensated geometry. There is the ability, Simufact has the ability to export an STL file of compensated geometry. So why do we need NTOP? Well, what we have found with a lot of our customers that are utilizing Simufact and other simulation, build simulation tools, is that compensated geometry, that STL file that's being created, is usually problematic. With complex geometries especially, a lot of customers have been seeing that the STL file has problems. It's broken. It's got, elements that are self-intersecting, and basically they're burning time repairing the STL file before they can get it to a state that it's ready to send to the printer for printing. So if you find yourself in that position, this very well may be the custom block for you. What you do with this custom block is you bring in a nominal geometry.unv file, and you bring in the compensated.unv file from Simufact. And we also point to the original body. In this case, this implicit body was brought in from a mesh, but it doesn't have to be. It could also just be the implicit body, nominal geometry. And inside this custom block, what's happening, if we open it up, is we see essentially that we bring in those two UNV files. They come in basically as meshes. We take the nodes between those and we are calculating the displacement vectors between the nodes. So the displacement vectors are simply a subtraction, right, from the compensated nodes and the original nodes. And that delta is basically creating these different vectors. Once we have those vectors, then we can bring in basically we can create a point map, right? And the point map is going to be those, it's going to be a displacement vector point map. It's going to be the XYZ coordinates with the different vector elements for each given vertice. Once we have that, we simply are converting that point map into fields, and then we're setting a bounding box so that the field is not super large and sort of infinite in nature. It's set to the size of the part, and we're smoothing it so that the smoothing basically will allow for much smoother transition between between each vertice. And then we're using what's called remap, and we're simply taking, for each direction, X, Y, and Z direction, we are remapping the original geometry to the new location per the displacement vectors at each vertice. So hopefully that basically makes sense. Like I said, you can always right-click on the custom block to look inside of it and see what's going on inside the custom block. So in this case here, this is the original geometry that we're seeing right now. And if I highlight this, the teal color is the compensated geometry. So the distortion that Simufact was predicting was in opposite direction and magnitude to the difference that we're seeing here. And so now this is pre-distorted so that essentially when distortion does occur, it's going to distort into compliance and very close to the intended nominal geometry. Now, I will also point out, if you are working with Simufact in particular, we have a great article. If you go to our support site, our knowledge base, and you look up how to import and use compensation data, this article shows you how to actually export the distortion data. So how to export those UNV files from Simufact to be able to use in this custom block. Okay, this article also does a great job of walking through the next example. The next example is essentially utilizing laser scan data. So the other scenario that we see and get questions about quite a bit is, okay, what if I'm not using build simulation software, but what if instead I'm printing the part and I'm measuring the distortion via laser scan, right? I'm laser scanning the parts and I'm seeing that the distortion is occurring. can I use that data? And the answer is yes, you can. So we'll go back to the software here and show you the other custom block, which is called Simulation Compensation Displacement Point Map Input. So in this case, what we're going to bring in is a vector point map. So normally what's going to happen in a QA environment is you're going to laser scan your part and you're going to end up with like a point cloud data, scan data of the part. And that is fine and dandy, but you need to use another piece of software normally to evaluate the difference, right? Evaluate the delta that occurs from the nominal geometry to what you just scanned. And normally that's metrology software, right? I've used in the past and commonly seen people using Polyworks as metrology software. There's other metrology softwares out there. They all basically do the same thing. They take that scan data, they have tools built in to allow you to align the scan data to the nominal part, right? So you're going to line it up with likely datums and reference frames, that sort of thing. So it's aligned. And then it's going to perform an analysis to measure the differences and how in or out of tolerance, the actual laser scan data is compared to the nominal geometry. Once you've done that, you can export from that metrology software a vector point map like what we're looking at here. These are all the vertices showing the vector elements, so direction and magnitude. And this is in CSV format. So the CSV would very much look like just a spreadsheet, just a CSV file of, 6 columns. X position, first column, Y position, second column, Z position, third column. And then the X, Y, Z components of the vector, displacement vector for each of those vertices in the next 3 columns. And that is the format that you have to get your data into. So sometimes there can be some data manipulation that has to happen when you export from your metrology software to get it in that format. But once you have it in that format, you can bring that CSV into NTOP just like this. And then we can use that to throw it into this custom block to produce our compensated geometry there. So again, compared to the nominal, we are now compensated in the opposite, direction and magnitude of the distortion, and ready to take this out of NTOP and send towards the printer. So what's going on inside of this one is very similar to the one before. It's just instead of us doing any kind of comparison between vertices of a nominal and compensated geometry, we're not doing that anymore. We're actually just taking the X, Y, and Z components of the displacement vector point map, breaking those into, or converting those into fields, and again limiting the field dimension and smoothing it, and then remapping it in the opposite direction is what's happening here. Now, it does stand to reason, if you have data, scan data, that is, for example, like aligned with the reference frame of the original part, and you had, vertices, basically, if you had CSV data of the original vertices and the distorted vertices, then we could likely use a good portion of what's inside the first custom block, and we could do that evaluation on scan data and make that happen. But that's kind of a case that I haven't really seen before in practice. So again, if anybody has any questions about this or wanting to develop something new and different, you have ideas about something else, I encourage you to reach out to your customer success manager or submit a request to NTOP support, and we will be sure to point you in the right direction to resources, or hopefully get some sort of consult going so that we can get you going on the right track. All right, thanks so much, and happy end topping.